All right, buffers. So a buffer solution obviously fits with acids and bases, and I'm sure you've heard of buffers before. So what a buffer is something that can resist changes in pH. Resist changes in pH. If you add hydrochloric acid to just a water solution, the pH reduces drastically as the concentration of H plus increases. What a buffer solution contains is some chemical in there that can react with the HCl so that it doesn't change the pH. Or the other way around, it also contains the ability to react with a base. So if we were to add sodium hydroxide to that same buffer solution, it would, it would have something in there that could react with the base so that it doesn't change the pH. Okay, so before we see that though, we're gonna talk about something called the common ion effect. So common ion is a shift in the equilibrium caused by the addition of a compound having an ion in common with something that is already dissolved. It follows what we know already about Le Chatelier's principle, if you remember shifting it back and forth in that last unit. We predict the shift by calculating Q. So consider this reaction. So we have CH3COOH, so that's vinegar, acetic acid in the organic form, carboxyl group. I keep stressing that. So we have plus water, we get H3O plus, and we get CH3COO minus. So acid, CH3COO yields the base CH3COO minus. Water is acting as then a base, becoming the conjugate acid H3O plus. According to Le Chatelier's principle, then what happens if you add more of this stuff? Well, we know what's going to happen is it's going to shift in the other direction. Why? You're adding a product, so Q is going to be greater than the equilibrium constant of K. And so in order to get back to K, we need, remember it's products over reactants, we need more reactants to make Q go down until it equals K. And so it shifts back to the left side. Now think about this in terms of pH. What happens to the concentration of H3O plus if we add CH3COO? Well, it's shifting in this direction, so that means the concentration of H3O plus is going to go down. And the fact that that goes down means the pH is going to go up because you have less H3O plus. All right, so this is the derivation of it. And I do want to show you the equation sheet and how we're going to use the equations on the equation sheet. Let me, this thing right here. Let me bring this down here so I can grab it. Okay. So this right here is our equation sheet. So this is right on our, something, I've been stressing, have it handy while you're doing it. We've talked now about a bunch of it. So it's under the equilibrium section. Here's our Kc, our Kp, Ka, Kb, Kw, and all the things it's equal to, pH, pOH. And now we're getting all the way down. We need this one today. And then you can see there's something in there, another P. So we have pH, but we also have pKa. But remember what I told you about P. P means negative log. So the pKa is the negative log of the Ka, pKb, negative log of the Kb. But we're not going to use this equation quite yet. So let me get this out of the way. And let's solve, we can actually solve these calculations without even knowing what the heck we're doing in terms of buffers, just by following what we've already learned. So I'm going to do letter B first, because letter B is, what is the pH if you have a 0.2 molar solution of CH3COOH? All right, so it's an acid. This is not a hydrolysis like yesterday. Remember, hydrolysis is with a salt, the conjugate acid and base from the reaction, and then which one affects pH. This is an acid. So we add this to water. It's a weak acid. We get equilibrium. We get H3O plus, and we get CH3COO minus. All right, so now we have an ice chart. Okay, so we got 0.2 to start with. We don't care about water, 0 and 0. I'm going to go through this quickly because this is, again, completely review. And if you don't know what I'm talking about here, go back and learn. I keep stressing this. I have a few people signed up today for one-on-one Zooms. I thank you for doing that. Come and talk to me so I can fix you. Okay, so we're looking for the pH. So now we need this right here. So the Ka is equal to 1.75 times 10 to the minus 5. We would look that up. I have it included here. Is equal to, I'm not going to write the entire Ka, I'm just going to plug in the x's, and remember we're ignoring that. So we get 0.2 times 1.75 times 10 to the minus 5, and then we need the square root. So x equals 0.00187. Little iced tea action. And then that is equal to the H3O plus, which then we can find the pH negative log. So negative log of our answer there, and we get a pH of 2.73. So if you have a 0.2 molar solution of acetic acid, the pH is going to be equal to 0.273. That's part B. All right, let's look at part A now. So we still have a 0.2 molar solution of CH3COOH, but now we're adding a common ion. So we don't care about the Na. Not only that, remember Na doesn't have any effect on pH, but we now have this CH3COO minus, which we have in our first reaction. So let me hit a reset. I saved this so that the equation would stay. So we have CH3 plus water. So the reaction is the same. Still don't do water. This is still 0.2. This is still 0, but this one's not. This is 0.30. So that's the difference. So we're not starting with 0 and 0. We're starting with 0 and the common ion CH3COOH or COO minus at a concentration of 0.3. Now it still has to go from left to right. We can't go from right to left because you don't have any of that. So it's still 0.2 minus x. It's still plus x and plus x. This is still x. But this one's not just x now, it's 0.3 plus x. Now, just like with the last one, I didn't check the percent ionization, but we're going to understand that we're always going to do this, at least in AP. So not only are we going to ignore the minus x for the reasons we have been, we're also going to ignore the plus x for the same reasons. It makes the algebra easier, and it is a good assumption as long as it's not 5% ionized. All right, so now our Ka value, it hasn't changed, 1.75 times 10 to the minus 5 equals x times 0.30 plus x, but we're ignoring the plus 3, or plus x, and then 0.2 minus x, but we're ignoring the minus x. Let me hit save again. You'll see why in a minute. All right, so now we're just solving for x, which is once again the H3O plus, and we're going to see how that affects the pH. All right, so 1.75 times 10 to the minus 5 times 0.2 divided by 0.3, and x equals 1.17 times 10 to the minus 5. So negative log, and we get a pH of 4.9. So you can see with the addition of the common ion, the pH went way up. It went up. It was 2 point something before. Now it's 4 point something. Why? Well, because the concentration of the H3O plus is reduced by the common ion as this thing shifts the equilibrium back to the left so that we equal K. All right, so that's the new part of this. So this addition of a common ion. Now we are forming a buffer solution. So what is a definition of a buffer solution? We already know the definition in terms of it resists changes in pH. But what it is a weak acid or base with its conjugate. So it's a weak acid with its conjugate base, or it's a weak base with its conjugate acid. In this case, it was the weak acid, CH3COOH, with the conjugate base, CH3COO minus. Now, if you recognize something as a buffer solution, going back to our equation sheet, this right here is called the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation gives us the pH of a buffer solution. It's a shortcut, as long as we recognize the fact that it's a buffer solution. Notice it's pH, so we're using the hydronium ion concentration somewhere there. We have pKa, so it's the negative log of the Ka, plus the log of Now the general form here is you have HA becoming H plus and A minus. So it's the weak acid HA and its conjugate base H minus. Now in our example, it's the weak acid CH3COO and its conjugate base CH3COO. All right, so let me use that equation. Let me hit reset again because I hit save again at a certain point, which was right here. So we got to this point where we did our ice chart, we plugged the stuff in. So now all this equation is right here is this equation if you take the negative log of both sides. So if you're good at logs, you understand what we're doing there. If you're not good at logs, just follow the equation. So pH equals, all right, so we want the pKa. So we're going to take the negative log, right? We're taking the negative log of both sides. So the negative log of 1.75 times 10 to the minus 5, and we get 4.76. Plus, now we need the log of the, so the formula is it's the log of the base over the acid. I think that's the, they have it as A minus, which is the base, over HA, which is the acid, base over the acid. So we're going to take the log of the molarity of the base over the molarity of the acid. Well, the base is 0.3 and the acid is 0.2, which if you can imagine, we're taking the negative log of both sides. So it's the negative log of 0.3 divided by 2. Now, when you're multiplying logs like this, though, there's a little trick to it. We got to add, so that's subtracted. So you can do the algebra if you'd like. I would prefer you simplify the algebra by, because when you divide logs, you know, you're supposed to subtract them. Divide 0.3 by 0.2 first, and then you can just take the log of 1.5. So 0.3 divided by 0.2, we got 1.5. The log of 1.5 is 0.176. So our pH is 4.76 plus 0.176, which notice is the same pH we got before. So if we recognize it as a buffer, all we have to do is that equation right there. We don't have to do any of this. Let me show you that. Next one. What is the pH of a solution containing 0.3 molar HCO3 or COOH? That's called formic acid. And then you have the formate ion with the potassium ion. So there's our buffer. We have the weak acid and we have its conjugate base. So pH equals the pKa plus the log of the base over the acid. So pH equals, we need the negative log of the Ka. So there's our Ka of HCOOH, formic acid. It's the chemical that's in the bites of fire ants, if you've ever been bitten by a fire ant. So negative log of 1.7, got an immediate coming up. I don't know if you can see that. 1.7 times 10 to the minus 4. So 3.76. So the pKa is 3.76 plus the log of the base. So what's our base? Well, this is our base, HCOO minus, which is 0.52, over the acid, which is 0.3. So let's divide those. 0.52 divided by 0.3. So we got the log of 1.73. So log of that answer, and we get 0.24, 3.76 plus 0.24 gives us a pH of 4. All right, so that's it for buffers. So try those practice problems I gave you. A little bit of review what we've been doing the past few days as well. And once again, sign up for that Zoom. As you saw, we got one in 10 minutes with some lucky student. We shall see how lucky they are. All right.